Hello, it's my pleasure to present my first seminar in infrared spectroscopy. And at the beginning, let me introduce myself. My name is Muhammad Alwi, and my scientific background includes Bachelor of Science in Genetics, Bachelor of Science in Biophysics, and Master of Science in Molecular Biophysics, and lastly, pre-PhD Diploma in Laser Metrology. Currently, I'm a PhD student at University of Ljubljana, interdisciplinary field of biosciences, and I was selected as a young researcher at the National Institute of Chemistry, and my PhD research topic will be mainly focused on using vibrational spectroscopic techniques for structural characterization of biomolecules. At the beginning, let me introduce the idea of the electromagnetic radiation. As we know, the electromagnetic radiation is considered as two mutually perpendicular electric and magnetic fields that oscillate in a single plane at right angles to each other, as illustrated in this figure. And this electromagnetic spectrum can be classified according to its energy, starting from left to right into gamma rays, X-rays, ultraviolet, and then visible region, followed by infrared, microwave, and lastly radio waves. And moving from left to right, the energy as shown is decreasing as the maximum energy at gamma ray and the lowest energy at radio waves, and the frequency also is decreasing and the wavelength, as we show, is increasing. These electromagnetic radiations, upon incidence on any material, can interact with the material in a mode that differs according to its energy. For example, if the lowest energy microwaves interact with the material, it can cause molecular rotations and torsion. A little bit higher energy in the infrared can cause molecular vibrations, which is of utmost importance for characterization of many materials, as we will show later. If the visible or ultraviolet radiation interact with the material, it can cause electronic excitation or moving the electrons from the ground state into a higher excited states. And lastly, X-rays can cause ionization or escaping of the electrons from the atomic structure. And what we can consider the most important for characterization of molecules is the infrared region, which actually can be classified into three main subregions according to its furtherness from the visible region. The first is the near infrared, which is near to the visible region, which extend from 14,000 to 4,000 centimeter minus 1 as a wave number, which is the reciprocal of the wavelength. Followed by mid-infrared region from 4,000 to 400 centimeter minus 1, and lastly the far infrared region, which is the far region from the visible region and extended from 400 to 10 centimeter minus 1. And it's noteworthy that the common used region for infrared absorption spectroscopy is That region extends from 4000 to 400 centimeter minus 1 because the absorption radiation of most organic compounds and inorganic ions is located within this region. Uh, Generally speaking, when the infrared radiation is absorbed by the molecules of a material, the molecules of the material vibrates due to the change of its molecular dipole moment. These vibrations of the molecules will be in a frequency that matches the frequency of the absorbed infrared radiation. In other words, we can say that the basic selection rule for absorption of infrared radiation is the matching between the frequency of the incident or the absorbed infrared radiation and the frequency of the vibration or the frequency of the movements or the vibrations of the molecule. When the frequency with which the molecules are vibrating is similar to or match the frequency of the incident photon, it will be absorbed. Hence, can cause a change in its molecular dipole moment. And generally speaking, these changes in the molecular dipole moments can result in two main categories of vibrations. The first, as shown in the first two vibrations in the first line, are called stretching, which involve bond length variation. It means that the bond between the atoms are stretching, the bonds are stretching or shrinking in a frequency, as we have said, that matches the frequency of the absorbed photon. This is the first type, which is called stretching vibration. It means increasing or decreasing the bond length. And this stretching can be logically even symmetric or asymmetric when we have, as shown in this example, when we have two bonds like that. These two bonds can stretch simultaneously in the same manner. This is called symmetrical stretching, or can when the first stretch, the second shrink, and vice versa. In this case, we can call it asymmetric stretching. And stretching vibration is considered the first changing type, which involve a change in the bond length. The other category is bending vibrations, which involve a change in the bond angle or the angle between bonds, and it includes mainly four main types or four main forms of bond of bending, which are as we show from left to right: twisting, or rocking, or wagging, or scissoring. These vibrations, it's noteworthy that these vibrations are characteristic for molecular structure. In other words, we can um, understand the molecular structure from these vibrations. Uh, but in order to do that, let us begin with the idea of vibrational modes. Uh, the definition of the vibrational modes comes from the possibility for any molecule to vibrate in many ways. Each way is called the vibrational mode. So we can say that the vibrational mode is the way with which any molecule can vibrate. In this regard, we can classify molecules, simply speaking, into uh, two main categories. The first one is diatomic molecules, are molecules that consist from two atoms, and this category can be classified into two subcategories, which are symmetric and asymmetric diatomic molecules. In the first one, asymmetric diatomic molecules means that the molecule consists of two different atoms, like carbon monoxide, for example. Uh, we have only one bond in this case, yes, that connects carbon to oxygen, and hence we have only one vibrational band, simply is stretching vibration, one stretching vibration. And this uh, one stretching vibration with a characteristic frequency that matches the frequency of the absorbed infrared radiation can be characteristic for this molecule, which is carbon monoxide, for example. Also, the other subcategory is the symmetric diatomic molecules, i.e., the molecules that are consisted of two similar atoms, such as Na2. In this case, there will be no change in dipole moment upon absorption of infrared, so it will be IR inactive and can be detected by other techniques such as Raman spectroscopy that will be discussed later. For other molecules that contain n number of atoms, we have two main subcategories also, linear molecules and non-linear molecules. And in order to determine the number of vibrational modes, the number of ways with which these molecules can vibrate, we can follow these two simple rules. For linear molecules, the number of vibrational modes equal 3n minus 5, where n is the number of atoms, and non-linear molecules have 3n minus 6 degrees of vibrational modes. And as an example of linear molecules is carbon dioxide. For example, carbon dioxide consists of three atoms, one carbon, two oxygen, in a linear form. So the number of vibrational modes is 3 times 3 minus 5 equal 4, which is shown in the figure. In phase stretching, this is the second one, in phase stretching, in which the two bonds are stretched simultaneously, and out of phase stretching, this first one, it means when the first bond stretch, the second bond shrink, and vice versa. This out of phase or asymmetric stretching, and two bending or mutually perpendicular deformations as shown in this and this one as shown by arrows. Also, as an example of non-linear molecules, we can consider water. Water H2O has two atoms of hydrogen connected with one atom of oxygen in a non-linear form as shown in the figures. Has 3 times 3 equal 9 minus 6 equal 3 modes of vibration. It means that water can absorption of infrared radiation at certain frequency can vibrate in three ways, three modes of vibrational uh, uh, motions, which are in phase stretching as shown in the second uh, figure. It means that both two bonds are stretching simultaneously, and out of phase stretching as shown in the first one. It means while the first bond stretches, the second one shrink and vice versa, and deformation, which involve a change in the angle between the two bonds. This is an example for uh, linear and non-linear triatomic molecules. And each vibrational mode among these vibrational modes can be done only in a certain wavelength, in a certain frequency of the incident infrared radiation, which matches exactly with the frequency with which the molecule vibrates. And this can be determined theoretically by following, for example, the spring mass model or the simple harmonic oscillator model. But apart from the detailed explanation of the simple harmonic oscillator that goes beyond the scope of our seminar, the information we can get from the infrared spectrum can be focused into two main information or two points. The first one is the number of the absorption peaks, which are related directly to the number of vibrational modes of the molecule. As an example, we have just talking about water, and we determined that we have three vibrational modes for water as a nonlinear triatomic molecule. The first is asymmetric stretching or out of phase stretching. This is its characteristic band, and this is the symmetric stretching or in phase stretching and the bending or deformation. In this graph or spectrum or infrared spectrum, we have 1, 2, 3 bands correspond to 3 absorption correspond to 3 vibrational modes of the molecule. And this is the first piece of information that we can collect from the IR spectrum is the number of vibrational modes. The intensity of the absorption peak is related directly to the change of the dipole moment and the possibility of the transition of energy levels. And generally speaking, each peak have its characteristic position that is characteristic for each functional group. That will be of utmost importance for characterization of biomolecules, as we will see later. So we can collect now the idea of vibrational spectroscopy in this very simple diagram, starting from infrared source which emits multiple of wavelengths in the infrared region that are passing through the sample. The sample will absorb the exact frequencies that match their vibrational modes and transmit the other that will be detected by the detector and presented on the computer. This is the simplest idea of vibrational spectroscopy, or the simplest idea of producing molecular vibrational spectra. And logically, the IR source and the sample chamber and the detector can be collectively uh, located in one device, which is the infrared spectrometer. But let's take a little bit detailed view inside uh, this device. We can say this uh, device in a little bit more detailed components. A simple representation of the dispersive infrared spectrometer as shown in the graph. But let me say that the infrared spectrometers, or the devices that measure and detect the infrared spectrum, uh, were developed through three main generations. The first and the second generations are called dispersive infrared spectrometers, and the last and the most modern one is the FTIR, or Fourier transform infrared spectrometer. And for this detailed discussion, we will consider dispersive spectrometers at the beginning, and we will show the development of the dispersive spectrometers into the Fourier transform infrared spectrometers. The first and second uh, generations of the infrared spectrometers, which are the dispersive infrared spectrometers, mainly consists, as shown in the figure, of IR source, followed by a monochromator and detector, and lastly a screen for presenting the spectra. The common IR radiation sources are inert solids that are heated electrically to promote thermal emission of radiation uh, in the infrared region of the electromagnetic spectrum. After that, the monochromator, which is a device used to disperse or separate a broad spectrum of infrared radiation into its individual neo-infrared frequencies. And lastly, the detectors, uh, which are devices that can convert the analog spectral output into electrical signal. These electrical signals are further processed by the computer, and this can be done using mathematical algorithms to arrive at the final spectrum that is presented on the computer. Uh, so we can conclusively say that in the dispersive infrared spectrometers, the story begins with emission of infrared radiation from the source, which passes through the monochromator that disperse or spread the infrared radiation into its frequency components, different frequencies in the IR region. These frequencies pass through the sample and the reference. The reference is the solvent, for example, in which our molecules of interest are dissolved, and we pass the infrared radiation through the reference in order to get their spectrum and subtract this spectrum from the spectrum of the sample in order to get the spectrum of the molecules and eliminate the spectrum of the solvent. After that, the infrared reach to the detector that detects the signal and present it on the computer. This is the basic idea of the dispersive infrared spectrometers. At this point, we can distinguish between the first generation of the infrared spectrometers and the second generation. Actually, the first generation of the infrared spectrometers, which is, as we have discussed, is a dispersive spectrometer. It means that it depends on dispersion of the infrared light into its frequency components. Use um, prisms that that are made of sodium chloride as an optical splitting system for splitting the infrared light into its frequency components. This is the core idea in the first generation, which was invented in the late teens. Um, and actually, this generation had some disadvantages related to the requirement for the sample's water content and the particle size, which were extremely strict, and also some limitations in scan range, which was very narrow, and its repeatability, which is fairly poor. These results in that the first generation of infrared spectrometers is no longer in use. The first generation is followed by the second generation of the infrared spectrometers and still a dispersive spectrometer, but instead of using prisms, the second generation used gratings as a monochromator for dispersion of the infrared radiation into its components of frequencies. Um, the performance of the second generation is actually better than the first generation, uh, but still had some limitations such as low sensitivity, low scan speed, poor wavelength accuracy. These encouraged scientists to develop the third and most modern generation of the infrared spectrometers. And in this point, it's noteworthy that the main difference between the first and second on one hand and the third generation of spectrometers on the other hand is the mechanism with which we separate the infrared radiation into its frequency components. As we have just said, in the first and second generations of the infrared spectrometers, we depended on prisms and gratings, or the monochromator conclusively. In the third generation of spectrometers, we replaced the monochromator with an interferometer, and this is the main idea of the third generation of spectrometers. But what is the interferometer and how it works? Uh, let's have a general look of the FTIR spectrometer, or the third generation of the infrared spectrometer. Starting from left to right, it will start logically from the infrared source that emits the infrared radiation, and as shown in the figure, it will pass through a very important component, which is conclusively called interferometer or Michelson interferometer. Michelson interferometer has a unique mechanism that enables us to uh, improve the performance of the infrared spectrometer. Uh, we will discuss the mechanism with which the Michelson interferometer later. After that, the IR will pass through the sample and detected by the detector and will produce what is called interferogram. We will discuss it later, and will be transformed by Fourier transform and presented on the screen. Let's have a zoom in look in the interferometer. As you can see in the previous slide, this part followed the infrared source directly is called interferometer, or Michelson interferometer is this. Yes, this is the interferometer. Now let's discuss the idea of the interferometer. Actually, in a typical interferometer or Michelson interferometer, it consisted of two perpendicular mirrors, which are this one, the fixed mirror, right, and the movable mirror on the top, and a beam splitter, which is a half transparent mirror. These three main components can do a very important function. Actually, the beam splitter is designed, this beam splitter is designed to transmit half of the light and reflect half of the light. Subsequently, the transmitted light and the reflected light strike the stationary mirror and the movable mirror respectively. When they reflected back by the mirrors, two beams of light recombine with each other at the splitter. This is the main idea of the interferometer or Michelson interferometer. The IR source, which is laser beam, emits a laser beam which pass through this half transparent mirror or the splitter, half of which will be transmitted through the fixed mirror and reflected again, and the other half will be directed towards the movable mirror and reflected again. The two halves will be combined at the splitter. and pass through and detected by the detector. By this uh, setup, we can notice a very important point. If the distance is traveled by the two beams, or by the two halves are the same, this means that the distances between the two mirrors and the splitter are the same. This situation is called zero path difference. It means that there is no difference between the path traveled by the two halves of the radiation or of the beam. Moving the movable mirror away from the splitter by a certain displacement x, for example, will cause the light beam to travel a longer path by 2x back and forth. Uh, Hence, the optical path difference will be 2x between the two mirrors. If the optical path difference is a multiple of the wavelength, logically a constructive interference occurs, because crests will match with crests and the troughs will match with troughs. So constructive interference will occur, and this will result in a maximum intensity signal that will be observed at the detector. In other words, we can say when the optical path difference, or delta, equal n lambda, where n equals 0, 1, 2, or any integer number, this situation will result in a constructive interference, and maximum intensity of signal will be observed by the detector. On the other hand, when the optical path difference equal half wavelength, this means the crest will match with trough, or the trough will match the crest. In other words, it will cause destructive interference, or minimum uh, intensity of light, or minimum intensity of signal will be detected by the detector. In other words, we can say the condition for destructive interference is that the optical path difference is equal to n plus half times lambda, where n is an integer number. These two situations are the two extreme situations, when the optical path difference is n lambda, and when the optical path difference is n plus half lambda. But when the optical path difference is neither n folds of the wavelength nor n plus half fold of the wavelength, the interference should be sum between constructive and destructive. In other words, the intensity of the signal will be between maximum and minimum. And since the mirrors are moving, since the movable mirror is moving back and forth, this means that the intensity of the signal will increase and decrease, which gives rise to a cosine wave. Let me show this very simple and illustrative figure. When the optical path difference 0 in the x-axis, when the optical path difference is 0, this means the intensity will be maximum. The optical path difference lambda by 2, this means that the intensity will be minimum. The optical path difference lambda, this means that the intensity will gain its maximum again, and so on. This cosine wave will pass through the sample, and this cosine wave will be detected by the detector, and this cosine wave is called interferogram, which is a relation between the optical path difference, or the distance traveled by the movable mirror, and the intensity. Or in other words, the intensity as a function of the distance traveled by the movable mirror. This interferogram, uh, thanks to the French mathematician Joseph Fourier, can be transformed using Fourier transform, which is actually a mathematical method for transforming one function to another function, can be transformed into an absorption spectrum. In other words, we can say that this cosine wave in the upper shape can be converted into absorption spectrum. This relation between the optical path difference or the intensity as a function of time or optical path difference, can be transformed into another spectrum, that is intensity as a function of the wavelength or the wave number, which is the absorption spectrum. Fourier transform is applied on the computer to transform the interferogram into absorption spectrum. So we can clarify the understanding of the FTIR spectrometer, starting from left. The IR source will emit the infrared radiation. After that, will pass through the beam splitter, half of which will be reflected to the fixed mirror, and half will be transmitted to the movable mirror. After that, both halves will be recombined again at the beam splitter and pass through the sample and detected by the detector in the form of interferogram intensity as a function of time or optical path difference, which after that in the computer will be transformed using Fourier transform into a spectrum or absorption spectrum, transmittance or absorbance as a function of wave number or frequency or wavelength, which is characteristic for the molecular structure of the sample. Conclusively, we can conclude the advantages of FTIR in the following 4 points. The first is the signal to noise ratio of the spectrum is significantly higher than the previous generations of infrared spectrometers. The second one is the accuracy of the wave number, which is high. In this regard, the error is within the range of plus or minus 0.01 centimeter minus 1, and the scan time of all frequencies is very short, approximately 1 second, and the resolution is extremely high. And due to these advantages, Fourier transform infrared spectrometers have replaced the dispersive infrared spectrometers. In a little bit more detail, we can summarize obtaining infrared spectrum by FTIR in the following steps. First, sample preparation, because among the advantages of FTIR or IR spectrometry is the ability to detect the characteristic spectrum of gas sample, liquid samples, and solid samples. In any form, we can prepare the sample, or we need to prepare the sample in a way that is most suitable for its form, whether it's gas, liquid, or solid. For gas samples, for example, usually we need a long, very long bath in order to compensate its dilution. For liquid samples, for example, we sandwich the liquid samples between two plates of NaCl or KBr, which are transparent to IR, the infrared radiation. Solid samples usually are grinded with uh, potassium bromide into a fine powder and pressed into plates through which the infrared radiation is passed. After preparing the sample, we can obtain the background spectrum. The background means the spectrum of the solvent or the gaseous molecules, etc. Uh, that should be subtracted away from uh, the spectrum of the sample. After that, we collect the single beam spectrum of the sample, from which we subtract the background spectrum, and after that we analyze the data, and this is done by assigning the observed absorption bands in the sample spectrum to appropriate normal modes of vibrations for the molecule. Uh, Unfortunately, I have came across a case study, which is a paper that have just published a few days ago using the FTIR spectroscopy for the detection of modifications in protein secondary structures as an indicator of radiation-induced abscopal effect. Uh, at the beginning, what is the abscopal effect? Abscopal effect can be defined as the shrinkage or disappearance of tumors in parts of the body that were not the direct target of the local therapy, such as radiotherapy, for example. In other words, when the local therapy or the radiotherapy is applied in a certain part of the body, other parts of the body can be affected, or the tumors in other parts of the body, of the same body, can be shrunk down or disappear. This is called abscopal effect. In this study, researchers used the Fourier transform infrared spectroscopy to detect the abscopal effect. And in this study, uh, they used changes in the protein secondary structure as a marker of the abscopal effect. And FTIR spectroscopy was used to detect these changes. It's noteworthy, generally speaking, that proteins give rise to 9 characteristic absorption bands in the FTIR spectrum, which are amide A, B, and amide 1 to amide 7. Here, the study focused on amide 1 band, Amid one band, for example, in the spectrum uh, extends from 1600 to 1700 centimeter minus 1 and arises mainly from CO stretching vibration with little contribution from CN bond. And also it's noteworthy that amid one band uh, is a broad band that consists of different components, each of which can represent a form of secondary structure, such as beta sheet, alpha helix, random coil. Yes. Uh, in other words, the amide 1 band can be analyzed into its components of beta sheet and alpha helix and random coils. In this study, the researchers used used mice treated um, with different treatments of radiotherapy. Uh, Four groups of mice. The first group treated with shame irradiation or shame irradiated. This means that they are not irradiated. The second one irradiated on the whole body of the mouse. The third one were cranially irradiated on the skull. The last group were irradiated on the lower limb only. For each group, the researchers recorded the FTIR spectrum for specimens from brain, lung, and kidney. Uh, the spectrum A and D represent the spectrum of the brain samples, B and E the spectrum of the lung samples, and C and F the spectrum of the kidney samples. The researchers conclude the results in this table, in which there is a significant shift in the amide 1 band position uh, in the brain samples in all the irradiated groups as compared to the shame irradiated group. As we can notice that in the shame irradiated, the amide 1 located at 1633, while in the whole body irradiated group it was at 1643. There is a slight change. Yes. Cranial irradiated, there is amide 1 band at 1643 also, and lower limb irradiated 1639. This means that upon irradiation there will be a change in the position at which the amide 1 band present. This indicates that there is a change in the protein conformation. This is the first notice. The second notice that this change in the amide 1 band position was occurred also In the last group, which is the lower limb irradiated only, it means that in case of irradiating the lower limb only, there is a change in the amide-1 band position in the brain samples. When we irradiate the limb, it can cause amide-1 band position changes in the brain samples. This can be as an indicator for the occurrence of the abscopal effect in the brain as a result of irradiation of the limb. In other words, when we irradiate the limb, the proteins in the brain can be affected. This is the first notice. The second notice is a slight conformational changes in the brain, and these changes can be attributed to its components of the amide-1 band, which, as we show in the red rings, the changes are located at the alpha helix, the positions of the alpha helix, the random coils, and beta structures only. These are the three components which experience shifts in the FTIR spectrum. This can be taken as an indicator of the conformational changes of the proteins involved in this treatment. Conclusively, the researchers concluded that the abscopal effect of the brain was detected using the Fourier transform infrared spectroscopy, and these data are consistent with the previous brain data, suggesting the conformational change in the brain in the protein secondary structure as a result of direct irradiation, and when the brain was abscopal to the irradiated region, or in other words, the lower limb irradiated group. To this point, thank you very much.